By how much will hydrogen gas diffuse faster than oxygen gas? A given volume of methane diffuses through a porous pot in 20 seconds. How long will it take equal volume of sulfur dioxide to diffuse through the same pot under the same condition? Arrange the following gases in order of increasing rate of diffusion. With this brief introduction, you're welcome to this video. I am Osas, the author of this channel, and in this video, we're going to give attention to Graham's law of diffusion. Graham's law of diffusion states that the rate of diffusion of a gas R is inversely proportional to the square root of its vapor density D. If you change this to mathematical equation, you will have R equals to K all over square root of D. In other words, R root D will be equals to K. Remember, when you change proportionality sign to equality sign, you introduce the constant. Now, if you consider two gases, that is, if you have the first gas and the second, then you have R1 root D1 equals to R2 root D2. Then bringing these equations in order and rearranging, you're going to have R1 over R2 equals to square root of D2 over square root of D1. Then recall that rate itself is actually the volume diffused. The rate of diffusion of any gas is the volume of that gas diffused over the time taken. So this is the brief introduction to Graham's law of diffusion. Don't forget too that density and relative molecular mass are also related. Relative molecular mass is equals to 2 times vapor density. So you can actually substitute relative molecular mass in place of density. And if that substitution is made, you have R1 over R2, that's the rate of diffusion of the first gas over that of the second gas, equals to square root of the molecular mass of the second gas over the first one. Now, let's give attention to the first scenario we presented at the beginning of this video. By how much will hydrogen gas diffuse faster than oxygen gas? Now, we do not have any information concerning the densities of these two gases, hydrogen and oxygen, but we do know the name of these gases, and as such, we will be able to calculate the relative molecular mass. For instance, the relative molecular mass of hydrogen, of course, hydrogen gas is a diatomic gas, so it will be the relative molecular mass of one atom of hydrogen times the two atoms. That will give us 2 grams per mole. Then oxygen gas again is also diatomic. It will be 16, the relative molecular mass of one atom, times the 2, and that gives us 32 grams per mole. Now, if you write out the Graham's law of diffusion and substitute, the rate of diffusion of hydrogen over that of oxygen will be equals to relative molecular mass of oxygen over that of hydrogen. Rate of diffusion of hydrogen over that of oxygen will be equals to square root of molar mass of oxygen 32 over that of hydrogen, which is 2. Then if you solve this equation, you will have rate of diffusion of hydrogen over that of oxygen equals to 16 all over 1. That is, you use this 2 to divide 32, you will arrive at 16 over 1. Square root of 16 is 4, square root of 1 is 1. Then this equation will further boil down to this equals to 4 over 1. Then if you solve this equation, making a rate of diffusion of hydrogen subject of the formula, you're going to get a rate of diffusion of hydrogen equals to 4 times rate of diffusion of oxygen. Therefore, we can simply say that hydrogen gas diffuses 4 times the rate of diffusion of oxygen gas. Yes, that was the solution to the first case we presented at the beginning of this video. One interesting thing about this video now is that I have a small ebook for Graham's law of diffusion and all these 3 cases associated with this application. So if you need the ebook, you can simply notify me in the comment section of this video. I will be dropping my email in the description box, so you can send me message either to my email directly or drop your comment in the comment section. I will reach you through there. So you can either use my mail or you drop your email in the comment section. Now let's look at the second case we presented. A given volume of methane diffuses through a oral spot in 20 seconds. How long will it take equal volume of sulfur 4 oxide to diffuse through the same pot under the same conditions? Now again, we do not have any information concerning the densities. All we do know is that the first gas is methane and the second gas is sulfur 4 oxide. Yeah, the first gas is methane and the second gas is sulfur 4 oxide. So how do we go about these calculations? First, we calculate the molar masses of the gases. The molar mass of methane is the molecular formula first of all is CH4. Molecular mass of sulfur 4 oxide is SO2. Now, if you calculate the molar mass of methane, you have 12 times plus 1 times 4. 12 is the molar mass of carbon, 1 is the molar mass of hydrogen gas. Because of the 4 atoms, you have 4 times 1, and that gives us 16 grams per mole. And that of sulfur 4 oxide is 32 plus 16 times 2, and that gives us 64 grams per mole. Now recall, we said earlier that the rate of diffusion of any gas is the volume diffused over time taken. So the rate of diffusion of methane, ROC, we are using ROC to represent rate of diffusion of methane, is equals to volume over time. And the rate of diffusion of sulfur 4 oxide, we are representing that by ROCS. That is equals to V all over T. We're using the same V because we were told in the question that how long will it take equal volumes. So we are using the same thing to represent equal volumes. Now, having done that, you simply state Graham's law of diffusion because this is an application of Graham's law of diffusion. All the information in the question is all boiling down or pointing towards Graham's law of diffusion. ROC over ROS, that's rate of diffusion of methane over that of sulfur 4 oxide, will be equals to square root of a molecular mass of sulfur 4 oxide over that of methane. So all the parameters we had earlier, substitute them here. You will now have V over 20, which is the rate of diffusion of methane, divided by V over T, the rate of diffusion of sulfur 4 oxide, equals to molar mass of sulfur 4 oxide 64 over that of oxygen 16. Now, if you change this division to multiplication, you invert this. So this thing will go up, V will come down. So you have this equals to square root of 16 over square root of 64 over 16. The next gas we had in the question was carbon 4 oxide. Calculate its relative molecular mass. We have 12 plus 16 times 2, and that gives us 44. We also have hydrogen gas, and that is 2 grams per mole. We've done this earlier. We have ammonia, and this is the relative molecular mass. Nitrogen is 14, hydrogen is 3. You sum them to give us 17. Hydrogen sulfide is 2 plus 32, that gives us 64. Now, having calculated their relative molecular masses, you now state your Graham's law. Remember, Graham's law is rate inversely proportional to square root of molar mass. So, since we are studying rate, to remove this constant, you can make it 1. And when you make K to be 1, you now have R equals to 1 all over square root of molar mass. Now, we will put the molar masses of each of these gases into this relation and check the behavior of R, that's the rate. Starting from sulfur 4 oxide, we have 1 all over square root of 64. That will give us 0.125. The next is rate of diffusion of carbon 4 oxide, and that will give us 1 all over square root of 44, and that's 0.15. We also have hydrogen gas. That's 1 all over square root of 2. That's giving us 0.7071. And of course, we have a rate of diffusion of ammonia, 1 over root 17. That's giving us 0.2425. And finally, the rate of diffusion of hydrogen sulfide, 1 all over square root of 34, and that gives us 0.1715. So what I did next was to prepare a small table containing the gases we just mentioned, their molar masses, and their rate of diffusion, so that we can see how rate of diffusion changes with molar mass. Now look at sulfur 4 oxide. Its molar mass is 64 grams. Its rate of diffusion is 0.1, at least 0.12. Then look at carbon 4 oxide next to sulfur 4 in the molar mass. The molar mass of carbon 4 oxide is 44 grams. Look at its rate, 0.15, much greater than 0.12. Now look at hydrogen sulfide. Its molar mass is 34 grams. Its rate of diffusion is 0.17. Again, bigger than that of carbon 4 oxide. Now look at the rate of diffusion of ammonia, 0.24. And of course, hydrogen, which has the least molecular mass, had 0.7 as its rate of diffusion. So what can we infer? What is our conclusions from this analysis? You will observe that as the molar masses increases, the rate of diffusion decreases. Or as the molecular masses decreases from 64 down to 2, the rate of diffusion increases from 0.12 to 0.7. Again, verifying or validating Graham's law of diffusion. That is all for this video. I hope you find value for this video. If you have been having any fear with regard to Graham's law of diffusion, fine, it is not out of place, but hearing me now in this video will be a great relief. If you need the ebook for Graham's law of diffusion, the book contains several examples and then approach to solutions with any type of problem involving Graham's law of diffusion. You can reach me in the comment section. Thank you very much for watching this video. If you are new to this video, please quickly subscribe to this channel because you can't afford to miss it. And for our returning viewer, thank you very much for believing in us. See you in my next video. Bye.